Okay, so today we're going to talk about balancing chemical equations. We've spoke on the different types that there are, and we've talked about how things can come together, things can be broken down, things can switch, but we also have to talk about how to balance them. And probably the first thing you're wondering is, okay, well, why do we need to worry about that? Well, there's this idea that things cannot be created or destroyed. And so when we're making these reactions and we're switching things around, we've got to make sure that we're being realistic. We can't just throw numbers around or throw elements around if they can't represent actually something that would actually happen. So we have to talk about something called conservation of mass, which is this idea that something cannot be created or destroyed. It's just this, it's a transitional thing. Things transfer from one type of energy to another, or they go into one form of mass then another. So things are not, it's not a magic trick. It's something actually that's really happening. So let's take, for example, if we write down an example here of an equation for a reaction, we have to deal with, like, let's say that we have sodium and it combines or interacts with iodine. Okay. Oftentimes, iodine, and there's lots of other nonmetals that normally will stay like this, where there's two of themselves all the time. Okay. Well, when they combine, it ends up looking like this. Okay. So one of the i's goes away. It only needs one of the i's, so one i goes out the door, and the other one stays. Okay. Well, this product. If that's the case, that wouldn't really make sense, because there's two here, there's two right here, and there's only one here. So what happened to the other eye? They can't just disappear. So one doesn't just magically go away. So if I want to be able to do this, I have to account for everything. The i's, however many there are, and however many NA's there are. So when I do that, let's just kind of make a checklist here. So for on the left-hand side, I've got one Na, and I've got two iodines. On the right-hand side, I've got one Na, and I've only got one iodine. So here I'm messing up here. There's something not right. I need to fix. So this needs to be fixed. I need to make it so that both these numbers are going to be the same. And the easiest thing to do is to make this number right here go up. Okay. So how we do this is this. We're going to place a couple of little spaces out in front. Okay. Because if I want to make it so that everything's the same, I have to make it so that everything on the right hand side has the same amount and everything on the left hand side has the same amount. So my NA's are fine. If you see here, they're both got 1 and 1. They're good. We've had the same amount of NA's. We're not performing a magic trick. We're keeping things real here. This is where it comes to play, where we have to fix something. So I've already got 2 iodines here, and I've only got 1 here. So the problem here is this. If I was to try to say, okay, well, I need 2 iodines on the right hand side, so I'm going to put a 2 here, that doesn't work. The reason why it doesn't work is because that creates a different type of compound. This is the compound right here. This one. This is the one that's going to be made. Okay, it's not going to change in anything else. It's going to be NaI. It just will be. So if that's going to be the case, and I can't make it to where it'll be different like this, maybe I can put a 2 in front of that. What does that mean? Well, it means this. So if I had just 1 or nothing in front of it, that means that I would have a compound that looks like this if it was just 1. So for 2 of them, now I'm saying I've got like this. I've got 2 NA's and 2 I's. Well, that's great. Now I've fixed my problem. I've made it so that now that 2 really distributes to both the Na and the I. So I've got 2 I's. So now I can rearrange this and say now I've got 2 I's. But here's the problem. Now I gotta say I've got 2 NA's. But look, now mine are not fixed. These are not right now. So I've got to change that. Okay, well, let's think. If I've got 2 NA's on the right now, I need to have 2 NA's over here. So I'm just going to put a 2 right there, and I'm done. Because if I go back and change and I relook and I say, okay, how many of each do I have? I have 2 NA's, have two i's, two a's, and two i's. So really, for a balanced equation, you have to have the same number of each element on each side of the equation. And that's really it. That's the whole idea of it. It just depends on what you're given in order for you to be able to do the problem right. So let's do another example. So another example we have would be, how about potassium iodide interacts with chlorine. And again, that's one of these, we call them diatomic gases, that will always start off with two of themselves. And when they combine, they switch, because this is going to be a single word placement. So the I and the Cl will switch. So the K will go with the Cl, and then you'll leave I on the outside. And again, if I is by itself, it'll normally be in this version where it has two of themselves. Okay. All right. So let's see what's going on. Let's see what we need to do here. So let's go ahead and write down. Okay, we got left, right, and we got the right hand side. So the left hand side, let's see what we've got. So we've got 1K, we've got 1I, and we've got 2 Cls. On the right hand side, we've got 1K, so that's good. We've got 1 Cl, that's a problem. Well, I guess I'll try to keep it the same here. I've got 2 I's, and I've got only 1 Cl. So these numbers are switched. Okay, so if you can pick whichever one you want, but you can see obviously that the problem here is iodine and chlorine. Their numbers are not the same on both sides. So let's look. So on the left hand side I've got 1, and the right hand side I've got 2. It's always easier to go up. So it's easier to make the left hand side have a 2 than it is for try to make this one a 1. That's not possible. So if I want to make this one a 2, well, I'll just put a 2 right here, because remember again, the 2 distributes to both the K and the I. Now it's like saying I've got, instead of having this, now I've got this. I've got 2 of these guys. So when that's the case, now I can change my I to 2. And then I can also make it so that now that 2 is in front of the K as well, so now I've changed that. Okay. Well, when I do that, now it means I've switched my K's. And normally when you have something that's switched because you've done something, like we put the 2 here, I would go ahead and try to fix it. So since you've fixed it to where 2 is now switched, try to fix K on both sides. So I had K on the left twice, and now I have 2 K's on the right, which fixes my K's. However, when you did that, your 2's now have affected not only the K, but now the Cl. So I need to switch. Now it means that I've got 2 Cl's on the right. Okay, well let's see. Do I need to fix that? I've got 2 Cl's on the right, and I've got 2 Cl's on the left. Well, if you take a look at all the numbers that we've got, they should all be the same, and they are. You've got 2, 2, and 2. And that's how you know it's balanced. If every element has the same number on the left side as the right side, you know you've done it right. Okay, because this makes it so that the conservation of mass has stayed true. We've not destroyed anything. We've not created something out of thin air. Everything's there accounted for. We've just been able to make sure we have enough of everything we need. So we've had to add 2 compounds of Ki and 2 compounds of Cl will end up being what is made in order so that we can have the right amount of iodines and the right amount of chlorines. Okay, let's do another one. Let's do one more. So this one's going to be a little trickier. It's going to be a little bigger, but we can do it. So let's do, for example, one that deals with polyatomics. No. And I'll try to write it small down here. Okay. So we got everything wrote out now. And then we're just going to try to figure out everything what we have. So what I would do is go ahead and write down everything you got on the left side, write down everything you got on the right side, and compare what you got. So CA is 1. Okay, I see 1 CA. Now, you can do it one of two ways. The easiest way to do this is to keep your polyatomics the same. So you need to get used to seeing. If you see SO4, okay, that is 1 polyatomic ion. So say that SO4 is, there's 1 of them. And that's true. You only see 1 SO4 here, right? So that's easy. Also, I see 1 Al, and I see 3 Brs. Okay. Also, on the right-hand side, I see only 1 Ca. I see 2 Brs. And I'm sorry, I'll try to keep them the same so we can write them down together the same. I see 3 SO4s. I see 2 Als, and I see 2 Brs. Okay, so let's see what we've got here. Looks like a lot of things are off. So this one's off, this one's off, and this one's off. The left-hand side does not match the right side. The only one that makes sense right now is calcium. So that's the one we're not going to worry about because we don't have to fix it. So what I would do is I would normally try to focus on your polyatomics just to get them out of the way. So when we do that, we see that, okay, well, we've got 1 on the left and we've got 3 on the right. So it's always easier to make the smaller number bigger. So what I'm going to do is I'm going to put 3 right here to make I've got 3 SO4s. Because again, this 3 says I've got 3 of these guys. So it's like saying, I'll erase this, but it's like having this, but having 3 of these whole compounds. So now I've got 3 SO4s, so I can change it. But when I do that, I change my calcium, which means I've got 3 calciums now. Okay, when I do that, I change my calciums. On the left-hand side, I've got to change them to the right. Okay, that covers everything, at least for the calciums and the SO4s, the sulfate. So let's see if we can fix our aluminums and our... actually, no, it doesn't, because we got to go back up here and say 3. Now we've got 3 calciums, 3 calciums. Okay, 3 and 3. Well, that affects my bromines. So this is a new thing, but we can say 3 times 2 is 6. If you think about it, Br2 looks like that. So if I have 3 of them, now I've got something that looks like this. So that means I've got 1, 2, 3, 4, 5, 6 Brs. So that's why I can say now on the right-hand side I've got 6 Brs, since I put the 3 in front of the calcium. Because remember, again, it distributes to both sides. So Br is 6, which means I got to make this side 6 on the right up here. So if I'm going to do that, well, what times 3 gives me 6? 2. So now I can change this to 6. However, since I changed this to 2, remember again that it goes to both numbers, so it means now that Al is 2. And that means that, oh, well, let's look. So the left-hand side's got to be 2. But look, and the right-hand side's got to be 2, but now they're the same. So it ends up being that all the numbers are right. If you look back, then we've got the same amount for every element or every polyatomic. Everything's good, and that would probably be your most typically your most hardest one. The only other ones that I could see maybe dealing with is a special case with combustion or something with a hydrogen or a hydroxide, but that's just a special case. So that's all we're going to do for now. I think that'll get you guys started on the right track. Please rewatch the video again when you start practicing these on your own to make sure that you're doing them right. Go back and watch the videos, make sure you're doing all the steps correctly. And thank you guys.